It is science in its most perfect form. While other great events, like the discovery of a polio vaccine, or the identification of radium, or the engineering marvel of the moon landing, are great scientific achievements, the harmony between pure mathematics and science has never been more perfect than our study of the transit of Venus. To the ancients and moderns, Venus was and is the most beautiful object in Earth's night sky. But Venus is also key to a great mystery which continues to fascinate us through its transit across the Sun. Although humankind long knew that Venus was a planet, a wanderer in the night sky, its transit became the key to unlocking one of the secrets of the universe. At its simplest, a transit is the act of passing over, across, or through, a passage from one place to another. In the case of Venus, it is the passage of Venus across the face of the Sun. It is similar to an eclipse of the Sun by the Moon, although Venus appears much smaller because it is much farther away from the Earth. The transits of Venus are one of the rarest of predictable astronomical events. During a 243-year period, only 4 sightings of the transit may be observed before the cycle begins again. The transit of Venus became the key to unlocking the mathematical elegance of the cosmos. Nicholas Copernicus and Johannes Kepler knew that the solar system was large. But how large? In 1619, Kepler figured out that Venus was about 30% closer to the Sun than Earth. Mars was 50% further from the Sun than the Earth. But how far was the absolute distance of Earth from the Sun? That question stared astronomers in the face and began one of the greatest scientific quests in human history. In 1639, British astronomer Jeremiah Horrocks was the first to observe a transit of Venus based on corrected calculations of Kepler's tables of planetary orbits. In 1719, English astronomer Edmund Halley proposed that the mathematics of parallax could be used to find the actual distance of Earth to the Sun. Parallax is the observed shift in position of an object when viewed from different positions. Surveyors use parallax or triangulation when they need to determine the distance to a remote object. If surveyors could measure remote distances, then why not astronomers? Halley believed that using parallax could answer the question of the distance of the Earth to the Sun. The average distance of the Earth to the Sun is called 1 astronomical unit. From this unit, we have a common way to measure all distances in the cosmos. Halley believed this technique of parallax would work for Venus because of its larger size and because Venus is closer to Earth than Mercury. His prediction was that the results would have an error of just 1%. But the problem is that the opportunity to collect data from a transit of Venus is incredibly rare. In 1769, astronomers were preparing to determine the parallax of Venus and the value of the astronomical unit with certainty. 150 observations of the transit were recorded, but there was another problem. It was discovered that as the edge of Venus approached the edge of the bright Sun, a black drop effect spoiled the exact moment of contact. The 1% error Halley was hoping for was not obtainable. Scientists and the world would have to wait another 105 years for the answer of the ages. In the 1870s and 80s, Jesse James robs a bank, 3 stagecoaches, and 3 trains. Barbed wire is patented, which will end the open ranges of the American West. Levi Strauss markets blue jeans with copper rivets, price $13.50 for 12 jeans. Thomas Edison patents the incandescent light bulb. And the public is wild about the coming of the Venus Transit. Even a march is composed by John Philip Sousa in honor of the event. Scientists travel to various locations around the globe to witness the transit of Venus. One such mission went to Hawaii on September 9, 1874, nearly a century after Captain Cook had charted Hawaii. A ship from England, HMS Scout, sailed into Honolulu Harbor, carrying an expedition of 7 astronomers. The mission of the expedition was, as Captain Cook's had been in 1769, to observe a rare transit of Venus across the Sun for the purpose of better determining the value of the astronomical unit and, thereby, the absolute scale of the solar system. Scientists had determined that Hawaii was an important place to observe the transit. Its island location offered an unobstructed 360-degree view of the stars, and the position of Hawaii near the equator afforded one of the best views of Venus. The team in Hawaii was well equipped. The astronomical apparatus sent to the islands included 3 transit instruments, more than half a dozen telescopes, clocks, chronometers, compasses, micrometers, and a photoheliograph. The Hawaiians, under their king Kalakaua, welcomed the expedition and provided sites and living quarters to the scientific community. The method of observing the transit was to record the precise times that the edges of the planet touched the edges of the Sun, twice as the planet touched the left side of the Sun, and twice as the planet touched the right-hand side of the Sun. The times between points A and B and points C and D would take about 20 minutes. From these points, as viewed from different positions on Earth, would be derived the distance of Earth to Venus. From this number would be applied the ratios set down by Kepler, and from the results of those ratios would derive the answer to which scientists had long waited: 1 astronomical unit. On December 8, 1874, the rain clouds withdrew, the sun shone, and useful observations were obtained at 2 of the 3 observing stations at Honolulu and Waimea. In England, the transit's aftermath included the laborious efforts to analyze the data and publish the results, an effort that encompassed many years. The American astronomer Simon Newcomb, formerly of the Naval Observatory, combined the data from the transits of 1874 and 1882 and numerous other kinds of measurements. Also, he looked at the orbital drift of the 2 planets, and he examined the shift in each of the observation points from Earth's rotation. From these calculations, he derived a value of 149.59 million kilometers for the distance between the Earth and the Sun. The answer was found. Earth's place within our solar system was confirmed to within 1 million kilometers of the value used today, as found through modern-day satellites and radar. Today we know how vast our galaxy is, and how tiny our place is in it. The majestic vision of the stars as seen by new images recorded by the Hubble Space Telescope beckon to the skies. As we see these images, scientists wonder again, how large is the universe?